you here. The purpose of this meeting is to allow researchers and Red Hatters to get together and talk about what they're doing and give each other input on their work. And we're very fortunate today to have two speakers from BU who were recently awarded collaboratory grants as part of the BU Red Hat Collaboratory. They're going to be speaking on new projects that are starting, and they're both in the areas strongly related to cloud network computing. So I will not take any longer in introducing them, except to tell you that our first speaker is Professor Alan Liu, who's an assistant professor from the Department of Electrical and Computer Engineering at Boston University. And the topic of his talk will be enabling intelligent in-network computing for cloud systems. And I will post a link to the notes in the chat here in case anybody wants to enter comments or questions in the notes. Thanks. Go ahead, Alan.
Sure. Thank you for having me here. So let me share my screen, I guess. There's some issues. I probably need to rejoin. Let me rejoin. Sorry about that. It asked me to rejoin.
So is the model here that we just interject with questions, or is this less?
Yes, that's the model.
Okay.
And I'm trying to record, but it's not responding to me.
I already have a recording, Heidi.
Oh, okay, cool. Thank you.
I started to record right as you started talking. I may have missed like
Excellent.
2 seconds of your
You're
intro.
so efficient. Thank you, Jeff.
That's what I'm here for.
Okay, cool. Go ahead, Ellen. We can see your slides now. So like we said, if anyone has sorry, I was on mute. If anyone has questions or comments, please speak up during the presentation or raise
It
your
looks
hand.
like you're muted too, Alan. Is he hearing?
Yes.
Oh, there we go. Perfect. Okay.
All right. So let me go back. So thank you for having me here. So I'm very excited to share some of my recent work in this direction, enabling intelligent in-network computing for cloud system. And please feel free to stop me anytime. So what I wanted to argue here is the following. So the networks infrastructure today in data center are becoming more programmable. What I mean is across the network passes, there's a different kind of devices there, like programmable switches. They can run different kind of tasks there. We have also, like in the server side and the end host, we have SmartNICs. They can run lots of certain computing functions as well. Or on the CPU side, we can run like software switch, etc. So this such programmability give us a new power. We can do certain functions and run certain tasks on top of the networks, and also create some kind of heterogeneity of how the network is performing. So given such programmability, one thing we kind of to consider in today's talk is what we are using it for, right? This kind of programmability is great, but why we care about it? One direction we are talking about here is about, can we get a visibility from the network to see, what's happening at every time that the traffic is going through the network, no matter it's the overlay network or it's a physical network. So this is the telemetry part. And once we have grabbed the important telemetry data from the network, we can do a lot of things. We can make a lot of management decisions. We can run certain functions, applications. So let me give us some very quick examples about certain scenarios. One scenario I can think of is For example, if there's happening some TCP/IP service attack or any DOS attack, like a privacy leakage, etc., we do need to identify these attacks, right? So one way, or the normal way we identify, is from the network traffic. We analyzing the network traffic to understand, oh, this is potentially attacker, or this is potentially could be a victim of the attacks. And then we have this information, then we can try to mitigate attacks. So all of this, like, we need the telemetry data. The second scenario I can think of, for example, in the distributed systems, in the storage systems, we have a lot of hotspots, which means some servers, because of the skewness of the workload, some servers are receiving a lot of requests. Some servers are colder. Some items are colder, so receiving fewer requests. So this kind of skewness in the workload creates load imbalance issue, right? So we need some telemetry data to quickly understand, for example, collecting, like in the ideal world, we know every key, how many times being accessed, where they'll be accessed. We aggregate all this data together. We should be able to figure out some kind of load balancing techniques, like a migrating or replication, to get the load balanced. So all of this, the key message here is we need to do the network telemetry at a very fine grained and a very real-time manner.
Alan, can I interrupt for a second? I'm not sure if you're changing your slides or not, but it's still on the title slide.
Already changing by a lot.
Yeah, that's what I thought.
Okay. Let me see if I can.
Just updated to example scenarios.
Yeah.
And also it's showing the mode where it has the small slides and the big slides instead of just presentation mode. So
Yeah, let me switch to the presenter mode and share this.
okay, cool. Thank you. Sorry, everybody.
All right, so I think now it's good, right? You can see my screen.
Yes.
You see my slides moving?
Yes, it's moving to networks are becoming more programmable now.
All right, so let me kind of go back. So I want to talk about here is the networks have become more programmable. Like you can see a lot of different type of devices, programmable devices that exist in the network passes today, like programmable switches, like router switches are programmable. You can modify the packet processing behavior. We have like SmartNICs and hosts and servers. We can process a packet the way that we want. And then at the CPU side, we usually have the software switch like OVS and VPP and BAS, or this kind of software switches. We can do the packet processing. So this kind of programmability here in the networks enables some kind of new tasks. As I mentioned, that one way we wanted to leverage this programmability is to do telemetry, because telemetry is so important. We want to understand what's happening to all this network traffic, and then we can, using this telemetry data, to inform and perform some management tasks and to support a variety kinds of cloud applications. So one example I just mentioned is, for example, for detecting the DDoS or DOS or any kind of other type of talk, like network attacks. So you need to identify the attacks through the telemetry data, what's going on in the network traffic, any flow has abnormal, behavior. All this could be a strong signal of attacks. And once we get this signal, we get this telemetry data, we can do kind of migration based on this, right? This is one example. The second example I mentioned is, okay, in the distributed storage systems, like key value store, etc., right? So we have a lot of hotspots, which means some servers are receiving a lot of requests. Some servers are not, because of the skewness of the workload, right? Some items are hot, some items are cold. So if we can identify quickly at real time that what items are hot, what items are cold, we can adopt a lot of load balancing mechanism to address the traffic to make it more balanced across the system, right? All of this, I want to deliver the key message is telemetry is the key enabler to this all kinds of management tasks we care about.
Alan, don't you give up privacy by making telemetry accessible? And how do you mitigate that risk?
So that's a great point, right? So one thing at the moment, we haven't really looked into the payload. So we are collecting data on the packet header part. So the privacy indeed a concern. Potentially the operator can get even infer some information from just the header fields. I think this requires some cooperation between the operator and the users, and some agreement that we should only collect certain data from the packet, right? So this indeed. So, but in this talk we haven't considered the privacy issue, but indeed this is a great angle we should consider.
I mean,
So
from black box packet data, you can actually reconstruct VoIP traffic, and lots of good stuff.
Right. So this is the deal, right? So we get more visibility, but at the same time that the user privacy is kind of a concern. But I think we need to find a compromise eventually, right? So we cannot like we connect no data. That is super private, but for our operational kind of purposes and for functionality, we do need to collect this data. So we need to find a balance and compromise that eventually, I think. So okay, so in the network telemetry field, there's a bunch of like a requirement we care about. So first of all, the network traffic variations. There's diverse and sometimes even unforeseen workload. Sometimes the traffic is normal. Sometimes you're experiencing burst from whatever, maybe from an attacker or from some flash events. A lot of people are accessing NBA games or like Super Bowl games that cause the burst of traffic. Or even because of the failure. This could be a variety kinds of causes why this workload can be varying a lot. And second is we do need to support different kind of tasks. What I mean task here is a lot of different metrics we collect. We not only collect some data point, we also need to collect the metrics. For example, at this point or this this particular time frame, what kind of heavy users, what kind of light users do we, for each user, how many distinct sessions you are maintaining, for example, video streaming sessions, and how long does your system is up. All these are metrics that we care about that for the up layer applications, they wanted to grab and get this data. The third part is, as I mentioned, we do want to, collect data and do the telemetry from variety kind of devices, CPU, IP, SmartNICs, and switches, etc. They have diverse resource constraints. So all this, the challenge and requirements that exist for network telemetry today. So then let's go back to the cloud model, right? Talk about network telemetry. So one example of a telemetry infrastructure in the cloud system is the Prometheus system, which is quite famous and used maybe by a lot of you at Red Hat as well. So it's become a data collector, a data storage by plugging a lot of data sources from like Kubernetes containers and different other kind of applications. You can collect like memory, CPU, even network connection, like time and volume. But they are lacking for example, lacking the visibility down to the network traffic level, like flow level. They are not identifying the network flows in a very fine-grained manner, which they don't support. Like, for example, can I get the network flow from one particular IP to the other IP with the different tags, like a protocol number, port number? All these are very hard to do in the Prometheus system. So. But alternatively, Prometheus is kind of a centralized collector. It has a storage. We can plug in some external data provider, for example, like a NetFlow, SFlow. They do certain things as I described. They sample the network traffic, they can get the flow level statistics I mentioned, like heavy hitters, distinct flows, etc. But there could be some issues. Even just plugging some, some existing data telemetry collection method. So one choice, right? One choice is even we don't do any sampling. We collect all the data from variety kind of applications as fine-grained as possible. So this creates a significant scalability issue. They couldn't scale to a lot of instances of Kubernetes and a lot of instances of the Prometheus. So one example, I heard about some public information from Amazon. They actually running. They are like the team of Alexa. They are running like hundreds of instances in some of the servers. And then they want to collect data at a very, very fast rate and do the forward capture of each data sample. And then they crash their system for like a half an hour at least after doing this. And then their Alexa become very dumb. They don't answer any like advanced questions. They only respond to like very basic questions. So this is one example I heard about from Amazon. If you do this for capture.
Alan, is the telemetry data collected out of band?
Yes, out of band.
Some other mechanism for collecting it?
So you mean for this particular one or the example I just mentioned?
Yeah, either. I mean, because otherwise the telemetry data collection actually interferes with your network traffic.
Right. So for example, it depends on where you do the collection, right? So if you do collection from the hardware switch, usually to for capture, you need to do the mirroring. You not mirror the entire packet, but you mirror the packet header fields to another port that is a vacant point that connected to some like data storage servers, and then they can capture all the data at a certain rate. But that is assuming that the server can catch up with the speed. But usually you need you need more than one server. You need a lot of server to cope with the high speed network traffic. So this is the type of band they're doing.
Just by looking at traffic. Well,
Sorry?
I'm derailing this, but can't you collect it passively just by looking at traffic rather than having to store all of these packet headers?
What do you mean like passively? But you still need to store something, grab it, and you don't want to interfere with the current data path traffic, right?
Yeah.
So the basic way that you read it and you generate something new and then you send it to the server. So basically it's a type of mirroring. You couldn't just grab the data, right? So to grab data, you need to create some new data that to be stored. So this is for the for capture part. And then people realize that this is the bottleneck. No one really do that for operational purposes. And then they do the sampling. That's the message I mentioned, that NetFlow, SFlow, they do sampling. They sample like 1 over 1,000 or 1 over 10,000, which Facebook was doing this type. But there's a lot of examples showing that if you're doing sampling of 1 over 10,000, your accuracy being hurt significantly for lots of the metrics they're collecting. And it's potentially a very bad idea. So then it leads to a large research train that would be my team and a lot of other folks in the community working on to design some custom sketches, custom algorithms to support certain tasks. For example, heavy hitters, distinct flows, and this kind of algorithm you might be hearing about, like a count min sketch or hyperlog, etc. So these algorithms are quite good in terms of supporting diverse workload. And then you need to carefully implement that into different kind of environment to catch up with different library requirement, resource requirement. So you do need to keep, so the algorithm itself is designed in a nice way, but implementing it is a challenge. So why is the case? Let me give us some background about the one particular type of algorithm I'm going to talk about today, sketch algorithms. So at the very high level, the sketches are just, it's the online algorithm. It takes input of a string of some unique items like packets, right? And then for this case, we have M packets with N unique items. And AABBC is the packets. So you fed this stream of packets into whatever device is doing the collection, like the routers or the NICs, and they will run this online algorithm called sketch algorithm. They only using very small amounts of memory. We call this usually sublinear algorithm, that they're using much smaller memory in terms of the size of the total data. And then there's a lot of fundamental work in the Siri community that they can, using this online algorithm to estimate a lot of different functions like heavy hitters, one of the most demanded tasks, or the estimating the entropy norm or L2 norm. A lot of work that in this space. But how does data structure look like, right? This is how it's being this online algorithm deployed. But at the very high level, one example how sketching works is for every data point, which is every packet, you grab some packet header field, for example, a source IP as the key, and then you hash this key, like this hash source IP address, multiple times using independent hash functions. And then you find the different locations in different arrays of counters. For here, we have our array of counters. Each array, we increment the counter in one of the random location based on the hash indexes. And then we do it multiple times. And then finally, we can just query this databases by running the same set of hash functions to get all this counters. That counters will represent, for example, the size of this key flow A, right? So this is one part of the heavy hitter. So if the flows are very large, like heavy hitter flows, we can query this and get the heavy hitter flows. So there's lots of analysis work and estimating this, tell you that the accuracy is bounded, whatever the workflow is, making it a quite attractive feature for using it as a telemetry tool. So then particularly today, I wanted to talk about how we can run sketches in software switches. So it seems like we have a variety kind of choices to run sketches, but we realize that even in the software platform, implementing this kind of look like a simple algorithm, it's not a done deal yet. So let me tell you why. So here we actually analyzing 3 different type of software switches that are popularly used, like OVS and the VPP, which is out of Cisco, and BAS is an academia product out of Berkeley. So we analyzing these 3 different kind of software switches, and we run sketches on top of them. But we realize that this after we applying the sketches, it creates, incurs a large overhead on the CPU, which can hinder the packet rate significantly. So this is one example here. We adopted the OVS DBDK. After applying, so here we have 3 sketches here, like a Unimon, Conmin sketch, and Con sketch, which you can consider just some 3 different sketch algorithm being used and developed from others and my team. So the sketches, it's dropped the performance significantly. So we want to do that. We don't want to do that, as Ari just mentioned, right? We are plugging this monitoring algorithm. It should not interfere with the speed and the normal traffic significantly. Is no one gonna use this tool. So, and then we rethink. Okay, it's not a done deal. So we put on the hardware, it looks fine, but in software, such a bad idea. And then we go back and try to analyzing if there's any issues that we can address. And we still want to adopt this very smart and resource efficient algorithm in our software platform. So we do some quick bottleneck analysis. So recall that we have much of hash functions, and after the hash functions, we need to update random location in the array of numbers. So these are top bottleneck that we identify using our profiler. So, and the hash was using at about 37% of the CPU, and the counter updates, use another like 15%. This is more than half of the CPU being used just these 2 operations. And then we wanted to think about, as academics, we wanted to think about how we can really improve the implementation of the sketches into the software platform. So let's recall, we can kind of model the entire algorithm and operation into 2 factors, like 2 numbers, P and H. Suppose that we deploy a sketch somewhere, we need to process P packets. And each packet needs to go through H functions. The H function can relate it to H hash functions. So in this case, we have 4 hash functions. So at a very high level, not so precise for the notation wise, we have total computation of P times H, right? So P times H. So we want to reduce that because you can see the figures a couple of slides ago that was hindered the performance significantly. So one thing we can think about is, instead of we can reduce the edge, right? So instead of we are keeping multiple hashes, can we just do 1 hash? So it seems like we can drop in the total computation to P. But it's not going to work. So one thing is this multiple hashes are a key factor or key idea that you can achieve resource efficient, to keep the memory efficient very high. So if we're gonna reduce the hashes to only 1, theoretically speaking, to keep the same accuracy as before, we need to use much more memory. So see how much more, like exponentially more. compared with the original data structure with multiple arrays of counters. And what is the issue? The issue here is if you have a significant increase in the data structure could be too large, for example, from like a 5 megabytes to 500 megabytes. That could, your 5 megabytes can easily fit into the last layer cache, but the 500 megabytes, most of the data structure is outside the cache. It can lead to like a very poor performance. Like per server, we are reaching, for example, 5 gigabits per second. Alternatively, right? So we reduce edge doesn't work. Then how about we reduce the P? So we reduce the P, then we can do some sampling. We do sampling to only process a subset of packets and update them into the old hash functions. What will happen here? So we actually still run into the same issue is we analyze this approach and we find that, oh, if we just doing the sampling over the packets, we still need significant more memory to keep the same accuracy as before. So at the high level, it's still missing a lot. You create a lot of cache misses, and it finally leads to poor performance. For example, 1 gigabits per second per server, without running any applications. So after we trying this two strawman solutions, we feel we kind of stuck here. So we stuck because of we have P times edge. We already tried to reduce edge, or we try to reduce P. Both doesn't work because it's actually have the cache misses issue. So, and then we try to think, can we rethink the way we're doing all this data structure with smart algorithms? We're trying to reduce the total computation into some S. That S should be significantly less than P times edge. So finally, we find a way. We find a way is like we rethink the way that we combining sampling and sketches. The second strawman solution, it seems viable, but if we can improving the memory and the accuracy trade-off, we might be able to adopt that. So we actually introduced an approach we call counter-based sampling. So we still process every packet. We are not sampling on the packets, but for every packet, we are not updating all the counters. But we're still keeping the same structure as before, but we're still keeping all these independent hash functions, but we only sample and updates a subset of these counters to be updated. So in this way, we effectively reduce the total computation P times edge into an adjustable value. So this is potentially can even be faster. For example, for a lot of packets, you don't even need to update any of the counters. You can skip, if in effect, that you skip a lot of packets. So we bring this idea together. We find, oh, okay. So eventually we can adopting this, we implement this idea, we increase a little bit memory, and we got significant performance improvement. So here, my key message here is with some simple algorithmic changes, our implementation can see a significant improvement, especially in the space of network telemetry. And then we implement into the OVS. And we also have other versions at open source. And then one example where we implement this the work nitro sketch into our pipeline in the OVS, and we adopt it and open source it. So in the long run, we wanted to talk about how we can adopt similar ideas into other platforms. So before that, and before running into some of the real numbers, I want to show you the performance. I wanted to kind of summarize the nitro sketch I just talked to you. So it's a counter-based sampling. It's not a packet-based sampling. With that, we only trade a small memory increase, which is constant factor of the sampling rate P, for a significant speed up on CPU. And effectively, by adjusting this P value, we can achieve much faster than a single hash table than in doing your data collection. So you're thinking about you're doing the data collection, you insert your key value store using hash table. We might even much faster than that. So it actually, this idea can be worked for a lot of other customer sketches, and we adopt that into our system. So And then there's some quick performance performance numbers. In this, we actually tested 4 popular sketching algorithms like UNIMON, CountMin, CountSketch, and K-array. We have an 40G data center networks with the OVS DBDK enabled NIC, Intel NIC, which is a cheaper one. I think it's also widely used. So we have 4 bars here. The red bars is the original performance after applying the sketch algorithms. But by enabling our Nitro sketch, which is the sampling-based approach, all without adding any additional resources, additional cores, all the switches we tested can reach the line rate, which for that NIC is 40G. But this is not the limit. The limit is we even further testing the single thread performance using a like kind of old CPU, many generations ago. And we can achieve a very, very high line rate. For example, potentially for one particular algorithm, CountMin sketch, its original performance is about 7 gigabits per second. And then after applying a Nitro sketch, we can achieve nearly 200 gigabits, which give us a lot of rooms to support like future 100G, 200G type of software network in the future. So all given all this, the technical details, I want to deliver key message here is programmable networks with different type of hardware really enable us the new opportunity to adopt this real-time efficient telemetry capabilities. And the lessons we learn is from the past and from the ongoing works is we really can adopt these new algorithmic changes for better implementations. So I'm very excited to work with Red Hat engineers, work with you, trying to figure out your platforms to adopt our very efficient implementation and adding new capabilities into the telemetry capability in the Red Hat software suite. So I'm probably ending my slide now. I'm happy to take any questions.
There's a comment from John Archer in the chat, Alan.
Yeah, let me see.
About using network taps for collection. Is that similar to what you were saying before about having an out-of-band method for collecting all of this?
Yeah. That's I think similar. The tapping it's not normally used, but the issue is it's still the scalability issue, right? You cannot tap all the traffic into the storage, and then no one's really do that. Also, as Ari mentioned, that if you collect all the data, it also has privacy preserving concern that not people won't like you store all the traffic they are doing. So yeah, that's type of the thing. And also there's not real time, right? You collect all the data, the space in it's large. You need to run the query. That query is too complex. You're probably running over months with the terabits of data. Then how you're gonna run the query very fast? But in our manner, we're always keeping this very small summary of the traffic, and we aim to integrate with Red Hat products and different kind of platforms. Then we can collect data with very low overhead everywhere. So that's the goal. But definitely, we need to consider the privacy. We need to make a good balance between that.
And in your experiment so far, are you collecting only in a single data center, or are you collecting in multiple data centers collected differently?
Yeah,
like, do you have a duplication of everything for each data center?
So right now we are not deploying into like a real workloads or real data center traffic yet. It's very hard for us, but we plan to, if we got given the opportunity, we really wanted to test it out. Currently, we actually host them on the public cloud. We run this anomalously collected internet traces like a CADA. They have a lot of data, and we replay these traces going to our collector and to analyzing the accuracy in traffic. So, and then compare the accuracy and the performance. That's what we're doing in the current test bed. But we do hope that with proper testing, with proper adjustment and implementation, we wanted to test it on the real workloads.
So there are ways to avoid telemetry, for example, with rateless coding or what have you, right? Or back pressure protocols. There are all kinds of protocols that by themselves adjust rather than having to collect telemetry, analyze it, and implement adjustments. Why this particular route? Why is there some obvious use case where the telemetry is more valuable?
That's a great point, right? I think so number one, the honest opinion is as we are building this telemetry capabilities for you, for example, we would really want to hear about your real needs, right? So I have envisioned kind of needs that you might care about, but definitely it's up to the engineer and the operational purposes what kind of metrics you need. The second is we do think the things actually has a lot of applications. As one mentioned is the load balancer applications. We want to find the larger flow that using lot of issues. We want to find some large overloaded CPU and servers. We can migrate and rebalance the load. We also care about some CDN company like Cloudflare. They're adopting telemetry to do the DDoS type of detection. Then we can decide to notify their customer saying, oh, it's time to buy our service and reroute traffic into their scrapping center for the clean up the traffic. All this are, start with some detection and telemetry capabilities.
True.
I saw the one more. I mean, probably before I switch, last point is indeed to deploy through a span port network tap or something else. Yeah, it's a great point. I think ideally we wanted to just deploy online the traffic data passes and just reporting the small summary through to the control plane or to the other servers. We don't need to mirror any traffic or tapping any traffic. The traffic goes through easily, but you compute some online algorithm that keep the summary. It's a kind of a new type of real-time domain of doing the data collection. Yeah. All right, I think it's time, use a lot of times, and I will switch maybe to Ashit.
Yes, thank you, Alan.
Thank you.
So Ashit Anbar is our next presenter, and he's an assistant professor in the Department of Electrical and Computer Engineering at Boston University, and he'll be talking to us about open source brains for large-scale autonomous systems. Thank you, Ashit.
Yeah, because the permission.
Everyone has to rejoin to present. Yeah.
I experienced
We'll
that
be back.
as well. Yeah.
Back in a minute. It's just to increase the suspense,
Uh-oh. Did we lose him?
We did, but I think he's coming back.
Okay.
It's making it extra suspenseful.
I guess to follow up on that, Alan, while we're waiting, if there are people who have other test beds at Red Hat that they're using for traffic analysis, are you interested in trying out sketches in those environments? Is that something you can consider doing now? And if so, how would you want them to contact you?
So yeah, I think I have my email and I'm very eager to contact with anyone who has a test bed, because we were working on specialized hardware, but now this solution is software, so it should be fairly easily to merge and deploy into any kind of software-based platform. We do want it to to see, how we can analyzing the traffic in a more efficient way, what kind of overhead it is. We are very eager to learn all of this. And we have some students actually working to release a new version of open source suite. And part of the Purist idea, so it's not this work, but Purist work, we are being actually upstreaming to the Intel DBDK package, which is one of the famous kernel bypassing library. We're adding a small telemetry capability into the packet processing library because it's really interesting, but I was surprised they wanted some kind of telemetry even in the packet IO part.
Well, I know we have a lot of testbeds and a lot of people doing experimentation with DPDK, so hopefully we can find some other places.
Yes, so it will be released as a sample application, a sample plugin that you have
cool.
optional, but you can enable it. Yeah.
Okay, great. Ashit says mic problems.
You can tell us some geeky jokes. Just kidding.
And another point I wanted to, before I should join. So we actually wanted to even further optimize the implementation. So I think we saw it's an open source product. We wanted to using AES and other type of acceleration. Yeah, I should.
Sorry about that. The microphone was not being detected, but I think it's okay now, yes?
Yeah, we can hear you.
All right, let me start. Just a couple restarts always help. So present entire screen. Is that how you do it? And then can I do audio? Yeah.
So a quick note that if you only have one screen, you probably wanted to enter the presenter mode and then switch back and then just share that presenter mode screen. Then
is the normal screen coming up now?
No.
Is anything comes up now?
It says present.
Let's see. Yeah, so actually I have two screens, but the one of them is being shared. Let's try again. What about now? So it says you're presenting your screen.
I couldn't see your slides.
We just get your picture and your name.
Okay.
There's usually an option for present a tab too, if you want to try that. Or a window.
Yeah, that's I'm trying the window, so I'm starting the presentation and then I'm sharing the window where the presentation starts. Let's try it again. Otherwise, I'll just share the whole screen. Let's see. Any luck?
No, it's the same thing again.
Let's do all. What about now? It looks good. Maybe. Better? Let's see. So I will.
Yeah, success.
Great. Yes, let's just step right into it. But so my goal today is to really argue that that open source development is beyond just educational and various reasons, great reasons to use open source development, is really very much needed as a necessary component for these large scale autonomous systems that I will show today. So I'll go to the next slide. Can you tell me if it is this coming okay?
Yes.
Great. Definitely want to thank our team, collaborators, and sponsors. And cover three main objectives today. So first, talk a little bit about challenges related to scalability in intelligent systems. and maybe explore a couple of directions of how to solve them through a collaborative development frameworks of learning from diverse data sources. And then I'll touch on some future directions in a collaborative training and privacy-preserving training. And I'm really excited about this type of a use case, because the systems that we are dealing with are systems that not just processing data for analysis, but they actually have interaction capabilities with the real world. So decision making, often in real time, for safety and navigation purposes, for instance. And this is such a great use case. The mobility use case is shown here in the images for cloud-based and open source developments. And specifically in Massachusetts, where we have very diverse roads, weathers, and drivers. So this is a great place to develop these type of technologies, whether it is an autonomous vehicle shown on the left. We also have various assistive technologies in a variety of domains as shown on the right. And I just wanted to mention that quickly because this is related to the open source development spirit. So we are developing this assistive technology platform for people with disabilities, from understanding how to do this in a standardized data collection manner and up to personalized assistance. So we call this Open Guide, and this is one of our ongoing effort and an example of how some of the intelligent systems that I'll show you today can be applied. So, we have this issue where there's some disagreement on why is this application specifically of mobility and navigation is so challenging. And it really depends who you ask. So I love Elon's optimism and greatly appreciate it. But if you ask, so it depends who you ask. If you ask him, then he would say, autonomous vehicles, autonomous systems are coming next year, pretty much every year for the last 6 years. Whereas Chris Urmson and some other noteworthy individuals actually recently adjusted their predictions from like 5 years down the line to perhaps a few decades from now. And the problem is I think people don't understand the challenges fully of this type of large-scale systems and its implications. And that's what I would like to talk about just briefly, just to contrast this with some of the current systems we have today. So Siri, we all love Siri. It gets things wrong sometimes, and if it does, I guess the implications are not so bad. So maybe it calls the falafel place instead of your parents. So it is not such a bad implication of a decision-making system, and this is just with a one-dimensional signal of audio. Similarly, we share photos, and maybe there's some intelligence capabilities of computer vision, and some people are missed. But in our case, this is really a situation of fatal implications if the system fails for any reason. So in this case, this is a real-world example of a Tesla. I love this example because there's so many edge cases on the roads. In this case, it's detecting traffic lights approaching the car, even though this is just a truck carrying traffic lights. In this more severe situation, you actually have a truck overturned, unfortunately, and the Tesla is just driving heads on to it without even stopping. So you can see how complex the implications are of such systems. This is a more case, maybe a simpler case, but we can see it just swerves out of control while trying to park. So it is we've never done this as a society. So it's good to kind of remind that deploy these type of systems that make these life and death decisions every second. And that's part of the reason why it's so challenging. But even a lack of a data point, could imply some fatal consequences. So this is a big problem. There's so many rare edge cases, and when we want to realize these systems, we want them to be widespread, we want them to be robust, so anybody can deploy these systems and benefit from their immense societal application. But this today, all of the systems that I know at least are have issues with generalization. What happens when we slightly modify the camera? What happens when there is a new geographical location? And part of the reason that this is so challenging to develop today, and I would argue is beyond the capabilities of any single entity today, is because of how costly it is to design these systems. So you have to instrument a fleet and buy cars and sensors and pay people to operate the fleet and leverage massive training, AI training resources to train this. So this is, I would argue, is some bottlenecks that I would like to tackle in this presentation. By the way, feel free to stop me if there's any questions, but yeah, I guess in terms of time, I'll swoop through. Any questions, I'm happy to answer anytime. So let me give you an example of how we've been solving and tackling this issue of mapping observations to action. So from the perception of these systems to the control, this can be solved using something called imitation learning. Imitation learning is a very standard and basic way to train large neural networks to take as input data observations, could be images, could be LiDAR, radar, and map them to decision-making and planning, as shown on the right. And it all comes down to collecting this data set here. I don't know if you can see my laser pointer, but you just want to collect a data set of a human driving, and you just imitate that human driver. This works nicely if you are in very simple Silicon Valley maybe type conditions. It's sunny days, it drives well. This is actually in a Carla simulation. We call this, it is an open driving simulation that we use to develop these and test these systems. But any kind of complexity today, you can see how the generalization is the bottleneck. So it will collide with a pedestrian and exhibit unsafe behavior just maybe because of a new weather or a new town. And as a result, or illumination or puddles, as a result, you have this unfortunate situation where these technological giants are amassing data, all of this long tail events, weathers, conditions. These are fundamental to training a robust system. And so there is this race of collecting who has the most data and collecting this as proprietary resource. These are not the only 4 cases I showed, Tesla and Uber. There's actually hundreds and hundreds of developers across various autonomy use cases that are collecting their own data, instrumenting their own platforms, redundantly collecting the same cities and views, and not sharing any of the data or just small amount of it. So I think some of the models are developed in an open source manner, but the actual model that's trained and the underlying data is not. And this leads to a high societal cost in the meantime. So I want to explore new ways to address this problem, make this development more efficient. A related effort is the Open Data Hub, which is quite exciting and relevant to this problem, where this similar approach, in a generic manner to solve any AI problem is proposed, but there are still unresolved challenges in how to leverage large amounts of heterogeneous sources, data from those sources, and even how to incentivize collaboration, I would say, among these organizations that I showed in the previous slide. So we propose this system that actually learns without requiring explicit collaboration. It is more of a inspired by how humans can watch other drivers and systems in their environment and learn from that as a third-person view. We call this the learning by watching framework. It is actually quite simple. So if we are the car in black and we're watching another car driving in front of us, why can't we use that data to train our car, our system? This could be a Tesla, for instance. Maybe we are Uber and we're watching autopilot Teslas and we want to kind of piggyback on their data. This is a form of sharing, yes, and collaboration. But it doesn't have to be that. So it can also be other humans in the scene that have no instrumented vehicles at all. So this is a form of scalability that I would like, and a scalability paradigm that I would like to see the field go towards. And unfortunately, current approaches to learning these systems, as I said, it's called imitation learning, do not enable this because they require a first-person sensor collection. So in robotics and autonomous vehicles, this corresponds to essentially operating the vehicle or the robot from their perspective. You'll see in this video, this is a beautiful video of training a robot to play ping pong, and you essentially have to take the arm and do it from their perspective. Whereas we can, and this restricts the data that we can use. But humans don't do this, right? So humans actually, even babies, they can watch other people perform actions, translate that into their point of view, infer the actions in their own point of view, and then execute this effortlessly. So why can't our systems do this as well when they do imitation learning and effectively augment their data set? So to include surrounding vehicles. So for sake of time, I will go quickly, but obviously there's tons of challenges with how to do this effectively, but we find this to be very effective. So how do you handle the fact that there's different perspectives and the fact that a different view might be missing a pedestrian or car? So there is some reasoning, careful reasoning of translating it to your view that needs to happen. There's tons of uncertainty in here. But let's assume we can do this. We can then incorporate these samples into our data set, as shown here with D, and expand it. So now it's not just our data, it's ours plus others, and then just train a neural network from that larger data set via imitation learning. We actually test this on generalization, harsh generalization among towns and weathers, as shown here on the left. So this will be one town. You can see it has a certain background. And then we test these cars and let them drive, which is a really, luckily in simulation, we can test this safely. We also test on new towns that have never been seen before and has new type of intersections where we want to adapt by maybe observing other cars very efficiently. And we find that by leveraging this additional data, we can not only, we can train systems to navigate in the real world, not just from hours and hours of data. There we go. But even just for 10 minutes. So you drive for 10 minutes in a new town and you capture data. I mean, this is so powerful if you're trying to do a new use case, a new assistive technology. If you're a student who's trying to, hey, I have a new idea. I want to deploy my system, but I don't have any data. Let's just sit at an intersection, watch some cars drive around, and we have this general navigation system. And obviously with more and more data, this kind of amplifies and augments, because instead of just having your data, you kind of multiply this by the number of vehicles that you watched around you. It can be other systems. It can be drones, and a much more scalable framework. I'll show you this final example in a totally new town, where it just adapts from one example to drive. This car has never seen how to turn in this complex intersection, and yet they're able to do it. It is able to do it. So this was kind of a nice idea, and then we said, let's extend it to even scale further. Even learn more free sources that are available, but maybe vast amounts of online data set, online videos, rich, diverse, freely available data like YouTube. And humans also watch YouTube videos to learn new skills. So we said, let's see if we can scale it even further. And this again requires us to rethink our paradigm, because we cannot just instrument vehicles, collect our data set in a handful of areas and train our model. But now we also have this large, massive data set that has just images maybe, but it doesn't have the sensor measurements, for instance, and the ground truth. It's unlabeled. How can we leverage this data in order to train a more robust model? If we can do it, it'll be so powerful because there is so much richness to it all over the world. People are uploading hours and hours of video data to YouTube. Why can't we use it to train a robust navigation policy? There are also some challenges. This is unannotated, unconstrained. So it is actually quite difficult to use this data in any of the existing systems. So I'll give you, if you wanted it in what I said in mathematical notation, there's this question marks here. We don't know the speed. We don't know what actions should be taken. And I would say this is even more harsh because YouTube videos may not contain the best demonstrations you can think of, right? So maybe there's some ways where the system should not behave, but we still want to use that data in some way and to increase safety. So the algorithm is called self-D. It is an iterative. We resolve these challenges through an iterative framework. It starts here. We essentially train a policy using a small domain data set, where this domain data set could be an online publicly available data set for autonomous driving. There are several. Or it could be a new use case that you collected just a few minutes of data for. That gives you an initial trained model. You then predict over the large YouTube data by sampling from the model. And that gives you something called pseudo labels. You use those pseudo labels because these are a form of label, but they're coming from the model instead of from a human. You use those pseudo labels to pre-train your model, get a larger data set for pre-training this model, and then going back to fine-tuning on your local or smaller data set. And you iterate through this until it converges ideally to an improved solution, which we found that it does, and significantly. So we see a significant reduction in error across cities. So over 10 cities that we're testing here around the globe, both in the US and even Singapore. And we see a reduction in error from the baseline model in prediction of the future motion of the car, including nighttime conditions. So these numbers are all significantly lower by using the YouTube data. This is also something that can keep improving as you have more and more YouTube data that you're watching. And the evaluation on Carla further supports this. Actually, we were asking this question, even small changes in the displacement error and prediction can significantly impact success rate, reduce collision rate, and increase route completion when you do this in a closed loop manner where you actually let the system drive in simulation. I love these results because they show how difficult this is. This is a complex maneuver real world situation. In example, in nighttime condition on the Waymo data set, in the rain. And you can see how the orange points are very well imitating the blue points, which are the actual expert human future trajectory that's available on these instrumented data sets. So Miami, it learned to drive in Miami just by watching YouTube videos, and Pittsburgh, all over the world. So this is the type of scalability that I would like to explore. And then I just have 2 more slides for future directions. So we talked about, so just to sum up what we talked about robustness and efficiency. It could have been implicit collaboration, or we kind of copy data from surrounding sources, or some amplification from other diverse sources like online publicly available sources. But that takes us an interesting step towards collaborating between some of these agencies and entities fundamentally on the model and the data level. And maybe I can just show one slide about where I would like to do this in the future, but we're kind of building, putting the components together to build towards something like that. So definitely want to explore novel ways for companies, agencies, even people, as shown here, like through this YouTube study, to collaborate. Maybe there are, but when we explore these new technologies, I want to see what is the trade-off with respect to privacy We looked at cases where the data is shared. What if it cannot be shared due to privacy? But using it can further improve scalability and accessibility of these models. What happens when the models are and the platforms are highly heterogeneous, and how do we aggregate resources across these organizations? So these are some questions I would like to explore, and ultimately integrate this with some of these amazing efforts like the Open Data Hub. So if you have any, so just for sake of time, I'll stop. But thank you so much for listening. I would love if there's any questions, comments, feedback.
So we've run a little bit over, so we may not have as much time for comment as usual. But if people are interested in giving you feedback or comments or questions, they can reach out to you in email, Ashid.
Sounds good. eonbar@bu. Thank you.
Okay. Great. Well, thank you both very much for presenting this research, which sounds really interesting and definitely different. And I hope we have a chance to see where you go in this in the future.
Thank you very much.
Thanks a lot. Thanks for joining us for Research
you.
Interest Group. Bye-bye.
Bye.
See you later.
Thank you. Bye.